So far, we are able to calculate the probability of limit state exceedance for a problem consisting of two independent normal distributed variables. In this module, we will look at linear limit state functions with several parameters, the so-called general case, and a method to handle nonlinear limit state function, which is the case in most real situations. We are still in these approximate methods sticking to normal distributed variables and primarily independent normal distributed variables. In the general case, the limit state function cannot be described by two random variables, load and resistance, but rather by a function of random variables x, a vector with n so-called basic random variables. However, we can still utilize the properties of the normal distribution in the same manner as we did in the establishment of the Cornell's safety index. The sum of many normal distributed parameters will also become a normal distributed variable. To write the function mathematically stringent, the limit state function becomes a0 plus a1 times x1 plus a2 times x2 and so on until an times xn. The expected value will be a0 plus the sum of ai times the mean value of the xi parameters. The standard deviation can also be established in the same manner for uncorrelated parameters and correlated parameters. With the linear limit state function, the Cornell safety index can be established as a function of these a parameters as shown. For correlated variables, the mathematics is slightly more complicated, but the safety index is still of the same type. A problem arises when the limit state function is not linear. As an example, the limit state function we used in the earlier simply supported beam case, if the breadth, height and length is also assumed as uncertain variables, the function is a nonlinear function. So let's consider a nonlinear limit state function g of x1 to xn, where xi are uncorrelated random variables with known mean values and standard deviation. If we use a Taylor series expansion to linearize this function, it can be approximated to the limit state function inserted x1 star, x2 star and so on, where star marks the point at where we are linearizing the function, plus the sum of xi minus xi star times the partial derivative function for each xi. The derivatives are calculated at xi star. The safety index can then be written in the same way as in the general case, where ai are now partial derivative function at xi. An important choice we need to do is at what point xi star to xn star we should normalize around. One such option is to normalize around the mean value for each xi parameter. This is called the mean value first order and second moment, or MVFOSM. If we look at our previous example with the simply supported beam exposed to uniformly loaded Q, we can establish the approximated and linearized version of this limit state function as shown here. First, we have the limit state function inserted all the mean values, and then we have the random variables times the mean value of the partial derivative function with respect to this variable. If we rewrite the result of this to establish the parameters a0, a1 and so on to a5, these would be as shown here. If we keep the same mean value and standard deviation for the yield strength and the uniformly distributed load as earlier, but introduce a mean value and standard deviation for the breadth b, height h and length l, and insert this into the formula for the safety index, we achieve a value of the safety index of 1.5. Earlier we got 1.49 when we were using only 2 stochastic parameters and the basic Cornell formula. Here we have introduced a little bit more uncertainty, and as such they are maybe not directly comparable, but still they seem to be rather close to each other. So in this lecture we have shown the general case of the limit state function g and the Cornell safety index for this limit state equation. We have further shown that Taylor series can be used to linearize nonlinear limit state functions. We call this the first order second moment or FOSM method, as we use the first order approximation to the nonlinear function, and we use the mean value and standard deviation, hence the second moment, to derive the safety index. If we choose to linearize around the mean value of each parameter, we call this method for mean value FOSM.